Yes, ma'am. I started.
Yeah, so Zonaki, welcome to this lecture series. And as all of you have seen, she will be speaking on technology-enabled explorations, a rich context for integrating computational thinking and mathematical thinking. And it's very interesting when I read computational thinking and mathematical thinking, I was actually excited. And I'll just give a brief introduction, which has been circulated, but I'll still read that out. Jonaki Ghosh is a professor of mathematics education in the Department of Elementary Education, Lady Sri Ram College, University of Delhi. Her primary area of research and publication is the use of technology in mathematics instruction. Uh, Beside that, she works also on the professional development of mathematics teachers and the inquiry-based approach in mathematics learning. She's on the editorial panel of At Right Angles and also part of the International Program Committee of the Asian Technology Conference in Mathematics, ATCM. She has set up the Ramanujan Foundation for Initiatives in Mathematics Education and is currently the Vice President of the Mathematics Teachers Association of India, MTAI. Jonaki, over to you. Of course, bio was longer. I'm just reading a shorter one so that we give more
Thank you
time to
so much.
Jonaki to speak. Jonaki, over to you.
Thank you so much. I'll just share my screen first. Is it visible?
Yeah.
Okay. So thank you so much, ma'am, for Professor Minati Panda for inviting me. So I think in this session, as the title also suggests, but I think we can just, we are a small group today, so we can just reflect a little bit on the goals of mathematics education. And first, I would like to present some examples of open-ended problems from different areas of school mathematics that middle and secondary school students engaged with. And then maybe we can discuss a little bit about computational thinking, mathematical thinking as modes of thinking, their interconnections and of their pedagogical implications. And then from that, we can sort of maybe have some suggestions or implications for the curriculum. So, so if we go back to the National Curriculum Framework, the position paper, which said that what is the goal of maths education, simply stated, it is the mathematization of the child's thought processes. And for many years, when I would encounter work with teachers and people used to ask that how do we, define this word mathematization? And somewhere I felt after looking at many things, and I feel that this definition by Hans Freudenthal is perhaps a very apt definition because where he says that mathematics is a human activity and the pupil herself should reinvent mathematics. So the emphasis is on reinventing mathematics. And during this process, the learner is engaged in an activity where experience is described, organized, and interpreted by mathematical means. So, how do we bring about, can we really bring about this reinvention? Can we give students this experience of how to reinvent mathematics? And why do we need to give them that experience? So, if we please do stop me at any point if you feel that you need to ask something or. Okay, so I think if we look at the nature of mathematics and the role of experimentation in mathematics. One of the goals of mathematics education in school level is also to attain procedural fluency. So, working with algorithms, applying methods. As children are taught these things and they have to sort of reproduce them in exams and so on. But I mean, despite everything, procedural fluency is important, but it cannot be the only thing in learning mathematics. The question is, should we present mathematics to students as a magnificent edifice, which is marvelous and stunning, and where results appear magically from apparently nowhere? So, is that how mathematics should be presented to students? The thing is that as a discipline, mathematics did not evolve in that way. And even the great mathematician like Carl Friedrich Gauss himself wrote that uh, his way of arriving at mathematical truths was through systematic experimentation. And history has testimony to many important results and very, very important path-breaking results which have come up because of experimentation and because people made a certain conjecture, and maybe many years later the proof arrived. And that's how mathematics as a discipline has grown. So just I want to take one example. So the prime number theorem, so basically, we know that we all know what are prime numbers, and prime numbers are introduced right at the primary level in school. But the fascinating thing about prime numbers is we don't have a formula or an algorithm which produces prime number. So, so mathematicians are always were always looking at the distribution of primes, how are prime numbers distributed, and I mean, as you look at larger and larger number, they seem to thin out. But way back in 1796, Legendre, who had access to tables of prime numbers, computed up to millions. And he noticed something very interesting about the sequence of prime numbers. And so he saw that, so if we use this symbol pi of x to denote the number of primes less than or equal to a number x, let's say, then we know, like, we can say pi of 10 is 4 because, of course, here pi is not the number pi, but just a symbol to represent. We can use other symbol also. 10, so the numbers within 10, that is before 10, that is 2, 3, 5, and 7. These are the 4 prime numbers. So therefore, we say pi of 10 is 4. And if you look at up to the first 100 natural numbers, there are only 25. There are 25 primes. So now this is a spreadsheet, a snapshot of a spreadsheet where we have put the powers of 10 in the first column. And if we are able to get the data, which is easily accessible now, the number of prime numbers less than or equal to this particular power of 10 is now in this column. So Legendre had access to this, and then after some experimentation, it was found that if you take the quotient of these two columns, so it's 10 upon 4 is 2.5, 100 upon 25 is 4, and so on. After a while, you'll see that the difference as x grows from one power of 10 to the other, the difference in this quotient is approximately 2.3. And then another function, the natural logarithm of x, also the natural logarithm of 10 also grows as 2.3. So it gave a hint that it led to this conjecture that maybe for x significantly greater than 1, we can say that this quotient x upon pi x can be approximated by the natural logarithm of x, or the pi x is approximately x upon natural log of x. So this today is of course known as the prime number theorem, and it has led to a lot of deep mathematics. And it is known as the asymptotic law of distribution of primes. So it doesn't give a formula, but it tells us how are the prime numbers distributed. And that's a very significant and important result. And this is something that, given a little spreadsheet and doing a little bit of computation, which is hardly anything actually, even a school student can actually have access to this important result. I mean, they may not be able to prove it or understand it very deeply, but at least they can see a pattern arising, and they can see, oh, okay, so this is one of the important results in mathematics. And there are many such other things which can be made accessible to school students also. So the implications are if experimentation, and if that's how mathematics evolved, and if experimentation is so basic to mathematics, then why should we keep this fact hidden in our classrooms? And shouldn't we incorporate that kind of experiment or some kind of experimentation in teaching of mathematics, and wherever possible, make use of digital tools and maybe computing facilities. So the important thing is that when you are using technology, a teacher cannot pose a regular question like the way they appear in textbooks. So what kind of tasks can be designed so that students, if they have access to certain kinds of tools, that they can, use the tool meaningfully? Uh, can we provide an experience where students work individually as well as in groups to present their work periodically? So, when students start exploring a problem and if they get motivated enough to do that, they own the project, they own that problem and they feel proud of it. And they want to talk about their explorations and findings. And of course, the teacher has to be a facilitator and has to keep giving feedback. And technology, if it is integrated wherever required, should only be used as a vehicle for exploration, for doing things which cannot really be done by paper and pencil so well. And, so if broadly, if this is the idea that we follow, and I want to also share a little bit about the cognitive aspects of the use of digital tools. So people have used in the research, mathematics education research, people are using terms like this, they have been using for some time rather, digital cognitive technologies. So all these digital tools that we have access to GeoGebra, which is dynamic software. We have computer algebra systems, very powerful systems, which also have free accessible versions, or even a simple spreadsheet, which is there on almost every phone or computer. So these serve as medium for mathematical activity because so on the screen of your device, it is like it embodies your thought process. It makes external the intermediate products of our thinking. And you can share, suppose you create something, you can share it with your students, you can share it with people, and you can share your idea. So technology has advantages. Again, of course, there is a caveat that you have to use it in an appropriate manner. And there are two very commonly used metaphors about the use of technology. One is that of an amplifier, and the other is that of a reorganizer. So, what does it mean to amplify? So, this can be true for any tool, I suppose, not just in mathematics. But the tool can amplify possibilities, bring about a greater range of ability to do things which you can't do by hand. It also provides opportunities to investigate similar situations at high speed and accuracy. So it can quickly generate graphs. It can create a table of values. So, student can quickly create some data and start looking for patterns, make observations from the data, focus more on developing insight rather than get into the thing of solving and, creating the data. Technology can be reorganized if so. As an amplifier, it gives you more access, because more and quicker access, and as a reorganizer, it gives you access to higher level concepts. So I've often experienced this whenever I've done certain kinds of projects with students based on certain ideas. Some questions will come up in their mind which ordinarily, perhaps in just a paper pencil environment, they would not have asked those questions, because they can see certain things and there is a natural curiosity or a motivation to, oh, if that were this way, what would I get? So those asking those what if questions. Uh, Technology also supports looking for patterns, identifying invariances, making and testing conjectures. So all these are very critical for engaging with mathematics. So given that there is possibility of this kind, uh, and also, okay, here I just wanted to make a comment about people are also talking about the big ideas in mathematics. So when we look at our curriculum, we see that there are there are curricular areas like there's algebra. People tend to think in that arithmetic, algebra, geometry, at higher classes, trigonometry, coordinate geometry, calculus. But of course, those are important curricular areas. But there are also certain concepts which we can look at. So, for example, number. Number itself is a big idea because you can plan your teaching around these big ideas. Pattern is a strand which runs across the curriculum, right from primary level to any level that you can think of. Because as you know, we know that mathematics is actually looking at patterns and patterns of various kinds. Uh, Equivalence. Equivalence is something very critical. It's not just in algebra, but in anything. Equivalence is a big idea. Functions, relations and functions, data representation, iteration, chance. So these are some, there are roughly people have identified 20, 21 big ideas, and the list is growing, ever growing. But these are big ideas are important because they help to connect different parts of the curriculum. So we don't necessarily need to teach these topics as in silos, but these big ideas help to connect, make connections across different areas of mathematics, even school mathematics. And they also kind of provide an organizing framework for teachers to plan their teaching. So now I would like to come to some exemplars of projects where, so some short tasks and some slightly longer projects. I mean, I have quite a few things to share, but I have selected two problems so that because given the time, it will not be possible to. So these are problems which students worked on. I wouldn't call them problems. These are areas or topics which they explored using, and wherever possible, some technology was used. What I will share today mostly uses spreadsheets, which is the easiest thing to use. In a way, spreadsheets don't have very low technical overheads. So there is even children who are not familiar with programming and coding can easily use a spreadsheet. And I think we all use spreadsheets for various work in our day-to-day work also. So one topic which I always felt should be within the purview of school mathematics is that of fractals. And the big idea that this could be centered around is the idea of iteration and recursion. Iteration and recursion is not so much there in the school curriculum. And now in the new books that are being written, uh, there is a attempt to bring this in. Um, so so then I just wanted to share that why should we look at fractals? Because fractals occur in nature and they're all around us. So if you look at this fern leaf, the leaf of a particular plant, there is a mid branch, and then there are smaller leaves around that. And if you look at this smaller leaf, it has yet smaller leaves, so there's some kind of self-similarity and repetition. Now, if you take a small little leaflet and you enlarge it, it will look like the bigger leaf. Similarly, in branching of trees, if you look at portions, a smaller portion, it resembles the overall branching process. Or if you look at vegetables, like the cauliflower, if you take a small portion and you magnify it, it resembles the whole. So essentially, fractals exhibit similar patterns in progressively smaller scale. So if you look at a scaled down copy, it resembles the whole. So this is there all around us in nature. And Benoit Mandelbrot was the first one who actually brought out this term. And it was clear that Euclidean geometry cannot explain nature. And so there is this very famous quote by Benoit Mandelbrot. He says, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." So this kind of encapsulates that we need a new kind of geometry to explore nature, and therefore, of course, it's a very well-known field now. But school children, it would find it difficult to explore, natural processes which exhibit fractal patterns. But there are some simple geometrical constructions which school students can easily do. And so like I've taken the easiest example because this is the one which is probably easiest to, visualize and understand. So if you look at the Sierpinski triangle, so what does this do? We are all familiar with what is an equilateral triangle. So a triangle like this, which has all three sides equal. So what I can do is, suppose I join the midpoints of the three sides, and I can suppose join the midpoint. So I'll get four smaller triangles, and I remove the center triangle. So there is a hole here now. Imagine that this is a cardboard piece, and I just make these four smaller triangles. and I remove the center triangle. And now I'm left with 3 small equilateral triangles. And I repeat this process again on all these 3 triangles. So again, I take the midpoints of each of these 3 pieces, join them, I'll get 4 smaller triangles and remove the center one. If I do it on all the 3, I will get this. So we call the first stage stage 0 because that's a do nothing stage. You don't do anything to the shape. And then from stage 1 onwards, you get one hole. Now you keep getting more and more. These white portions are holes, so they don't exist. And if you keep repeating the same thing on all the triangles that are there, very soon we see that by stage 4 itself, it becomes fairly intricate. And students find this very exciting because they start counting like, okay, how many triangles do we have now? How many blue triangles are there? And so on. So one interesting question, of course, so you can just ask students, give them this drawing pattern and they can make, we don't even need to give it to them. We ask them to actually construct it. So there are many ways to construct these. And you get special dotted sheets on which they can do this work. And then they say, oh, okay, now let's count what would you like to explore about this? So they say, okay, can we count the number of colored triangles? And some children are very excited by what about the part which is white? So holes which are not there, how much has been cut out actually? If I'm using a paper cutter to remove these white portions, what exactly, how much is being cut out? So one natural question arises, ki how many triangles are there at every stage? And secondly, how much, if the original triangle is, let's say, 1 square unit, then how much is colored at every stage? So then children start speaking, they're saying, okay, it's getting lesser and lesser. Because it's the same cardboard piece, I'm doing the same thing to it. At every stage, I keep removing parts of it. So obviously, the area is getting lesser and lesser. So the conversation starts that way. And then we can ask them that, okay, why don't you draw up a table and write down the stage numbers, and along with every stage number, write the number of, it's not black, it's actually blue here, blue triangles and the shaded area. And they soon see that the number of triangles here you see is 3 in stage 1. Each of these 3 triangles give rise to another 3. So 3 times 3, that is 9. So you can actually count. Up to stage 3, it's easy to count the triangles. So we get powers of 3. And they soon notice that there's a multiplying factor of 3 as you go from one stage to the next. And little older students who are in, let's say, grade 9, grade 8, and grade 9, they can do this much. They can conclude that we ask them to find the general term or the nth term of the sequence. They see that the exponent is coinciding with the power of 3 is coinciding with the stage number. So we can say that at any given stage n, the number of small triangles will be 3 raised to the power n. So this itself becomes a powerful thing to arrive at. But if you look at the shaded area, so at stage 1, it was, let's say this is 1 square unit. And this at stage 0, it is 1 square unit, and it is divided into 4 parts, and you remove one part. So it's 3/4 of what was there in the previous stage. And the same thing continues. So what is here in stage 2 is 3/4 of. So this thing is not that easily obvious to them initially, but older students get it. But little younger students, they need some time to think about this. But if they've dealt with fractions and they understood fractions, then they're able to say that yes, this will be 3/4 of this. And then they see that we have sequences these are called geometric sequences. So these are powers of here we have powers of 3, here we have powers of 3 upon 4. And we do have another rule for the shaded area. And then it goes on. So we can also introduce the idea of why these formulae or these rules are critical, because it tells us why are they useful, because they tell us at any stage I can tell you what will be the number of colored triangles. So, but the recursive rule tells us that for any given stage, the number of triangles is 3 times the number of triangles of the previous stage. So articulating that in a symbolic form is also a very important part of mathematics. So recursive rules are not that much introduced in school curriculum, but it's a very easy thing to do because they are seeing it happening. They are seeing that at this stage 3, for example, the shaded area is 3 by 4 raised to the power 3, and the previous stage was 3 by 4 square. So you just multiply the previous stage by 3 upon 4, and this can be written in the form of the nth stage and the n minus 1th stage. So you develop a facility with symbols, and this part broadly about grade 9 and grade 10 students are able to write these recursive rules and understand what they mean. So after this, okay, so we know that it's very, we saw in the previous slide that even at stage 4, it gets very complex, very intricate. And but there are it's very difficult to draw the Sierpinski triangle at a very large stage, and because you need very sophisticated programs for that. And Mathematica is a software in which this is of course freely accessible on Wolfram Cloud. You can just enter this command Sierpinski mesh n, and if you put a particular value of n, it will give you that particular stage of the Sierpinski, also known as gasket or sieve. So one interesting thing is that, when we ask students, okay, can you tell us what stage this is? So any guesses from the audience, what stage this might be? You can there's no right or wrong here as such. You can just,
6 or 7?
yes, this is stage 6. So any way how you thought about it?
I think that's somebody else. Let's wait for somebody else to say.
Sorry?
No, maybe we could wait for somebody else to say.
Sure. Would anyone else like to argue whether this is stage 6 or 7, and basically how can we
Ma'am,
so
I
if you
would like to try. I don't know
yeah,
if it's
please,
right.
Isha. Go ahead, Isha. Yes.
Uh, uh, so you count the number of triangles. So that comes out to be 6. So that's how the white ones
Oh, the
basically.
white ones. Yes.
Yeah.
Very,
So
very
that's
good.
how.
Hmm. Okay, so you are
I mean,
saying that
we did it in class. We did this in
yes,
class.
I was just going to
No,
ask if
that
you remember
reminds me.
in core
Yeah.
maths, right?
So,
Yes,
yeah, core maths,
correct.
Sierpinski triangle, Ghosh snowflakes, all that
Yes,
you taught us.
yes. So the whole purpose is that younger children, so the students, like you just said yourself, that if you look at the biggest hole, it appeared in stage 1, right? And then the next sized hole is, let's see if I can. This is the next sized hole, which would appear in stage 2. Of course, there are 3, but if you just look at one sequence of holes, so this is the first one in stage 1, this is stage 2, this is stage 3, this is stage 4, stage 5, and a very tiny one is showing here. If we count that as well, so stage 6. So of course, we don't. So there are children who took initiatives, and I don't know if in your batch, but children have a great. They want to make displays. There's a lot of artwork possible using fractals, and
I was one of those. Like,
yes,
I enjoyed doing the artwork around it. Like, the
right,
mathematics part, like, after 2, 3 times I could follow, but I actually, like, drawing part and putting it in the file, I used to enjoy more of that.
right. So that's
Yeah.
true. Some students like to do these things, using a tool, a digital tool, because now we have tools like Mathigon and all, where you can put triangles together and make small stages and join them to make bigger stages and all. Uh, but this kind of a diagram also helps you see, like we talked about a cauliflower, right? If you take a small portion and magnify it, it looks like the whole. So where is the self similarity in this picture? So basically, if you look at the big one, if this is stage 6, I can see 3 copies of stage 5. And which is that? This is one copy, this upper triangle. This is the second copy, and this is the third copy. Within that, within stage 5, I can see 3 copies of stage 4. And within stage 4, I can see 3 copies of stage 3, and it goes on like that. So that is recursion. This is recursion in action and you can visualize it. And recursion is a very important thing in mathematics. So, so children have a lot of fun in doing this. But the problem is that, you can't visualize this after, even in Mathematica, a powerful software like Mathematica, if you ask it to do stage 8 or 9, it takes a long time. So how do we get a big picture understanding of this fractal? What's happening as the stages become very large and so on? And later on, we ask what happens as n tends to infinity, right? So one thing, simple thing could be that, you just draw up a spreadsheet and you incorporate the areas, I mean, the number of triangles and the shaded area, and you graph. So maybe quickly I can try and show you that. So can you see the spreadsheet? Is the spreadsheet visible? Yeah, okay. So, so we know that the number of triangles at any stage is 3 raised to the power n, where n is the stage number. So I simply do 3 raised to the power, and the stage numbers are in this column. In the first column A, I've just put 0 to 20, let's say. I suppose I want to know only up to stage 20 of the Sierpinski triangle. So this, and the area we had already said that the formula is 3 upon 4 raised to the power the stage number. So instead of typing n, I'm just clicking on the cell which has the stage number. And now I can select both these. And because there's a column to the left, I can just double click on this and I get the data up to stage 20. So children get fascinated even though, 20th stage, oh my God, such a big number, and I can't even read what that number is, how big that number is. And then, of course, you can just select this, insert a simple graph. There's nothing complex. You just insert a line graph, and you can see that graphically you can discuss the same thing, that the number of triangles is growing very fast. I mean, for younger children who don't know the terms exponential and other thing, they use, oh, it's growing very fast. And if we do the same thing for the shaded area, so this seems to be going. So of course they do see the numbers are reducing, because if they're familiar with decimals, they can see that it starts with 1 and keeps reducing, and then it becomes very, very small. So two opposite things are happening as the stage numbers are increasing. So some basic exploration of this using multiple modes of representation. So the same thing we are looking numerically, graphically, symbolically, using those formulae, and pictorially looking at the pictures. So the rule of 4, as they say. So for for understanding all these things, you need to visualize, you need to see numerically, you need to see graphically. And these multiple modes of representation are important even for developing algebraic thinking, so to speak. And so it doesn't end here. I mean, if you really just take the Sierpinski, there's so many things which are associated with Sierpinski triangle that it is quite amazing. And so there is this one with one group, I don't know which batch it was, but with one group, so again, my experience has been with BLH students in first year who come after class 12, but some of them have had mathematics up to grade 12, but many students are now coming who haven't done mathematics in 11th and 12th. So they visit mathematics after a long gap. So you have to do things with them which excite them, and sort of make them remember things also, and also see the excitement of mathematics. But
Ma'am,
in school,
Anushri has made some comments.
oh, I'm sorry, I am not really able to see.
So she has written in the chat box that
Can you please
does
read it out?
checking the side length reduction help in the same? The side length of each smallest triangle decreases by a factor of 2 per stage.
Correct.
Anushri, you can unmute and ask yourself.
Yes, yes. Should I go back to the diagram?
Yeah. I mean, this was just like a different way. So we were looking at the triangles,
Yeah.
like one way of doing it. But I was thinking, so in each stage,
Mm-hmm.
the length of each smallest triangle seems to decrease by a factor of 2. So I think, I'm guessing we can also
Okay.
like at some
Yeah,
level.
so you're saying if this is 1 unit, this is half, right?
Yeah.
And this will be half of half.
Yeah.
So 1/4. Yes, absolutely. This will
Yeah.
be 1/8.
Wow.
Yeah.
Nicely, amazing.
Again, there is a geometric sequence. So whatever attribute you take in a fractal, it will lead to some geometric sequence. And I used to teach geometric sequences in school using fractals because otherwise, if you just present a sequence, oh, 1/2, 1/4, 1/8 is a GP with common ratio, this and that. Students, okay, they get it, but I mean, there's no motivation. But here you can relate it, right? So I feel that I mean, if you're teaching at least in grade 11, if you're teaching the topic of geometric sequences, fractals should come up. Yeah, so thank you for pointing that out. So, and now, and there's something called the chaos game. So let's come back to the equilateral triangle. And so this is something, again, students of grade 8, 9, I've tried it on some occasions, and by then they have just learned the definition of probability in school. So they know that when I roll a dice, the probability of getting any one of the numbers 1 to 6 is 1/6. I mean, they know it as a theoretical this thing. Whether the understanding of empirical and theoretical is there, but they know that is. So now we are saying that there is this triangle, okay, equilateral triangle if you like, and we have 3 vertices. Let's label them as T, L, and R. Top vertex, left vertex, and right vertex. And I start with any point inside the triangle. Let's suppose I start with A. This is just a diagram to explain. So I roll the dice. So if I get 1 or 2, so I move halfway towards the top vertex. So I hope it is clear. So I start with A, and if I get either one, suppose I roll the dice and I get a 2. So I have to move towards the top vertex. So I'll move halfway. So I'll just imagine that there's this dotted line. I take the midpoint. Now B becomes my new point inside the triangle. Now I start from B, again roll the dice. So suppose this time I get a 3. 3 means I should move halfway towards this left vertex. So and mark the midpoint. Now C is my new point. So I keep rolling the dice, and the dice will tell me which vertex I should move to. And I keep generating points inside the triangle. Okay. So is that clear why we would get points inside the triangle?
Yes. That's nice. That we do.
So let's say we keep doing this, and let's say after 200 iterations, something like this is visible. Okay. So there was some starting point, and then of course, this is a GeoGebra simulation, but you start saying, oh, अच्छा ये तो यहाँ पे तो white है बिल्कुल. And then it starts clicking you. Something clicks inside, and you keep doing this. So what you are doing is you're just rolling the dice. I mean, you can simulate this through a computer program or through GeoGebra, but you can get other programs which show this. But if you do it up to, let's say, 1,000, what do you see?
Beautiful.
Sierpinski triangle. And this ever-present Sierpinski triangle comes up in many things in the school curriculum. Like if you take Pascal's triangle, they study Pascal's triangle, right? And I think we did it in core maths also. And you just, color the odd numbers and you leave the even numbers white. Again, you get the Sierpinski triangle. I don't have the picture right now with me. But so what is happening? Now you're relating, there's something going on, right? So older students can study this more deeply, but the younger ones can at least get the thrill of it. That kuch to ho raha hai. And here you can link the topic of probability to this fractal by this manner, that you can make some simple questions on probability. That suppose I start inside the triangle, what is the probability? So suppose in stage 1 I have 3 triangles. Let's call them T, top triangle, left, and R, L and R. And then at the next stage, so children enjoy this also, naming each triangle has a name, right? And each triangle has an address, so to speak. So if this is the top triangle and it is divided into 3 parts, this also has a top, left, and right. So the sequence of alphabets will exactly tell you So another fun game what one child devised is he brought a Sierpinski triangle up some stage 4 or 5, and he marked some of those little triangles and said, okay, can you tell the address? You have to identify the labeling of that. That they made a quiz out of it and all that. Okay, so that is just the labeling part. But suppose a die is rolled repeatedly, what is happening? Each new point will reside in one of these subtriangles. And so if suppose first time I get R, that means the point will be inside the R triangle. And then it is followed by T. T means I have to go to the top vertex, halfway to the top vertex. So suppose I start somewhere here and I get to the top vertex here. So the next point will lie somewhere here, and this happens to be the triangle TR. And from TR, suppose the points are, and the probability ensures what was the probability? Because my dice, I was saying if I get 1 and 2, I move to the top. If I have 3 and 4, I move to the left. And if I have 5 and 6, I move to the right. Right? So the probability is ensuring that where the point will reside, in which triangle it will reside. And then, you can, then you can modify this. And we ask children that, okay, can you think of the Sierpinski triangle, think of this, and you can modify. How can you change the game, rules of the game a little bit? So then one child actually said that, what if I don't want to take 1 and 2? Suppose this was one modification suggested, that if I get 1, 2, or 3 on the dice, then I move to the top vertex. If I get 4 or 5, I move to the left. And if I get 6, only then I move to the right. Now the probabilities are different. Earlier it was that it's equally likely for you to be able to move to any one of the 3 vertices. But now these are changed. So what would happen? Would you still get the same Sierpinski pattern, or would you get something else? So something is unknown. Something is there, but it's not clear what it will be. That is very important. That suspense is very important in the class. And then we can give simple questions. I mean, simple, which in the sense that which students can say, can you compute the probability of arriving at triangle R of stage 1 in just 1 roll, or arriving at this particular triangle in stage 3 in 3 rolls? So they can multiply the probabilities and get the answers. But again, there's another, so related to this, there's another interesting thing, is that you can simulate. So now we are saying that I don't actually want to roll the dice because it gets cumbersome after some time, but can I simulate it? And simulation requires you to write some complex program. Not complex, but some programming is needed. But something very simple can I do, which every child can do. So one possibility is that, so the question we are asking is that in stage 2, there are these 9 angles, and these are their names. So how many times on an average do I need to roll the dice so that I get pairs of letters which in a manner which covers all these 9 triangles? Okay, so is the question clear? The question is that what is the average number of rolls? I mean, how many times do I need to roll the dice? Because see, if I get, suppose I say 1 and 2, if I get 1 or 2, it is T. If I get 3 or 4, it is L. And if I get 5 or 6, it is R. So each time I roll, I get an alphabet. I either get T, L, or R. But I may get 2 T's together. I may get T followed by R and so on. So how many such string of letters will I need? Or how many rolls will I need so that I can cover all the, I mean, I'll be able to get all the triangles of stage 2. So let me show you this. I hope I can show you. I can discard this. There's also something called the chaos game. So here, do you see this? I hope the numbers are visible. So what we have done is, here the top row is the die rolls, right? So I randomly select, so Excel has a random, and most spreadsheets have this. It's called rand between 1 comma something. So if you say rand between 1 comma n, you will get a integer between 1 and n randomly, okay? So it's 1 and 6 because I'm rolling a dice. So suppose I get 2, 4, 2, 1, 6. I've rolled it about 20 times. And each time 2 translates to what? 2 should be T, because my rule was that 1 or 2 should be T. 4 should be L. Again, 2 is T, 1 is T, and so on. So how do I do this? First, I just take ran between. Now, please observe what is happening to here. This is just a simple command which has been put, ran between 1, 6. Now I'm dragging this. What did you observe? The numbers have changed, right?
No, I can't see that. No,
No?
I can't see the screen, anything moving. I mean, your
Oh,
screen is
no, but
frozen
you
for
can see
me.
the die rolls. I mean, you can see the spreadsheet.
I can see the spreadsheet here.
Okay.
Yeah.
Okay, now
Cursor is
just
moving.
note,
No
let
actual
me,
Movement.
can you see the numbers? 1, 4, 5, 4. Oh,
1,
maybe.
5. Yeah, there is the simulate the game using spreadsheet. That screen only is there.
Oh, you can't see the spreadsheet then.
That's a
No,
spread
ma'am.
that has part of it is a
Oh,
spreadsheet.
no.
We are
Sorry,
still on
sorry.
presentations. We can't see
Oh,
the spreadsheet.
why is that happening now?
Okay. So she is actually
Can you see now?
no same thing.
Oh,
We don't have any nothing changed.
just a second. How did this happen? I have to show you the
Ma'am, you
spreadsheet.
have to share again with the spreadsheet.
No,
Or you can say
I didn't need
yes.
to do that earlier, no? Just a second.
So if you share your just a tab, only that would be open, and even if you go move to a different tab, it won't be visible for us. So you have to share the entire screen.
हाँ, the entire screen का option मुझे नहीं पता नहीं क्यों नहीं
That
मिल
is
रहा।
called share my computer or share that. That's the first one, which will actually whatever changes it will keep showing. I should go to. I wouldn't have the.
See, now you can see the screen, right?
Now
This
we
is
can
the
see the screen,
presentation.
but it
And
is
can you see the spreadsheet now?
a task. Let's play. That's all. That is the.
Oh,
That's actually the
no, for
your.
some reason,
def-
I don't think I'm doing, but oh, I stopped share again. 1 second. So I go to share. When I go to share, there is this thing called Microsoft.
Share screen. No, you if you click on share screen, what that?
There is nothing called share screen. That's the problem. I'm not getting
Oh.
it on.
Oh.
Okay, अभी क्यों नहीं आ रहा?
Now that is going.
Sorry. Now?
But now I can see that the
Some,
presentation is kind of half gone. Half of it is there.
It is
but
stuck.
maybe
The spreadsheet is not visible.
I can see half of it, probably.
I can't see the Excel sheet.
Ma'am, please stop sharing and start again.
Wait. I don't know what I'm doing wrong, but I've done it all along. I don't see what's going on. Wait. So,
We don't use spreadsheets. I really don't know how to help you.
acha. See, it
If you
keeps
can
on.
open the spreadsheet on a different window,
It
and
is
then
there on
share
a
that.
different window only.
Yeah, and like you can just click on that particular window and share that, and then you'll have to go back to the presentations again.
Okay, so I think I will not keep doing. Now you can
Now
see,
we can see the spreadsheet.
but you will not be able. And what about this? Oh, okay. So you can't now see the presentation, but this doesn't happen in my, okay, anyway. So let's look at the spreadsheet only. So now you can see the die rolls, right?
Mm,
1, 4, 5, 4.
right.
So now if I, because the command, the ran between 1, 6 is here. So if I now drag this, the entire thing has changed. A new set of 20 roles have come up, right?
Mm-hmm.
And they get translated to like 3 is L, 6 is supposed to be R according to the rules. And this can be brought about by using a simple if condition. Like you say if B1, that is this cell is 1 or 2, then you give you give the possibilities. and it translates. Now we start working backwards and we see that suppose my last two letters are LR. So I quickly shade, note that in stage 2, what is the triangle LR. Then I come to LL. Then I come to TL. So I keep taking pairs. This is just done to help see the last. So the last two pairs letters is LR, then LL, then TL, then RT, and so on. So how many roles will I require till I'm able to identify all the uh, triangles of stage 4? So students play this game on the spreadsheet, and each child does it differently, and they count the number of roles required, and then the average of that is taken. So roughly it is supposed to be around 24, but I'll come back to the, sorry, presentation. Now I've lost that.
You have to share again, I think.
Why is it not showing me that? Now I can't see the PowerPoint on my this thing. It is
No,
only
we
showing.
also don't see, so you probably have to share it again.
No, but see, the choices are not there. No? I should get the presentation as well as the Excel as two separate windows to choose from, right? I don't know why that is
No
not coming.
options. Acha, I have a no.
Strange, actually.
Now it's moving. The spreadsheet is moving. Ma'am, you have to select your presentation and then share. Like you have to open on your laptop.
It
So
is
before
open.
you click on share on Zoom, if you
Yeah.
have, if you keep the, you open the presentation
It is
and
open,
then
yeah.
you come back and click on share, the tab should be visible.
Let's see. Yeah. Now it is. You're right.
It's visible now.
Yeah. Okay. So this is of course this was a on this. That's why I was wondering that you were thinking it is this, and I was actually trying to show the actual spreadsheet. Okay. So this is just a snapshot of that. So this kind of simulation helped students to create a game out of this. And okay, so there are a lot of things one can do with fractals, and these are some things created by our students. These are called fractal cards, greeting cards, which they're very easy to make. You fold and you cut. So you have to take certain measurements, you fold and cut, and you keep repeating it on smaller and smaller pieces, so that so when you fold and cut, and then when you open up the card and you push out the cells, you get to see. So this resembles it's kind of a 3D version of the Sierpinski triangles. I think you can see that there are three parts to it, which are copies of each other. And students were asked. So one important thing is that students are asked, given the project that is given, is that okay, you've studied some of these fractals and their properties. Now you create your own fractals. Create something, some other pattern or design which has self-similarity embedded in it, and cull out the mathematics from it. So one such was, this is a known card. I mean, it's called a fractal card, this one, which is different from the Sierpinski. And this particular student said, I'll try something different. And she tried to create another version of this, which had two copies of. And then the mathematics, of course, changes. So they counted how many cells at each stage, what is the size of those cells, and how much area do they cover when you flatten out the card. So many topics of area, perimeter, length, number of cells, all these things led to different attributes and, of course, different explorations. So, and this is not something which is very difficult for everybody to do. But yes, the practice can get complex. So the easier ones can at least be looked at by younger students also. So I just wanted to give one example of the fractals and mention that, the mathematical processes involved are counting, engaging with recursion, generalization, and sort of, if we try to keep in mind that counting the number of triangles, line segments, looking for the simpler patterns can be done with grade 7 and 8. Uh, so you have a I don't like to put them in two separate bins like this, but the fact that we finding the formulae, expressing the patterns in terms of the nth term and the recursive and explicit rules is very much a part of algebraic thinking. But visualizing those and making sure how you would simulate it on a spreadsheet, that part, how would you write the simple, how would you use the command so that you will actually get, for example, in this, we had to translate 1 and 2 to T and 3 and 4 to R and all that. So what command would you use and how would you structure the command so that it gives that output? That part is more computational. And then looking at, geometric sequences and various things. More importantly, looking at these things numerically, graphically, symbolically, and even through the pictures. So there is integration of both computational and mathematical thinking. The second example I wanted to take was, again, there will be a problem in switching to the spreadsheet because without the spreadsheet, this isn't much fun. But okay, I'll try. So there are many such problems which are interesting and which can be discussed in the class. And these problems are more suitable for secondary students and older students, 9 to 12, let's say. So there are many, but today I thought that I will discuss this briefly. So anyone, are you familiar with this problem?
Yeah, vaguely.
Yeah. Monty Hall, also known as the three-door problem. So so this is a very old problem way back in the 1950s, So there used to be this game show, and basically there are three doors, and there is the host of the game show is his name was Monty Hall. So Monty, there are three doors. You suppose you are the player, right? You see three doors, and behind one of the doors is the prize that you would like to win. And behind the other two is either empty or here just for fun, they say car and goats. So the car is the prize and the other two have goats. So so you pick a door. So Monty asks you to select one. Monty of course knows behind which door is what. So he asks the player to choose. And suppose you are the player and you've chosen, let's say, door one. This is just a picture, huh? So don't get confused. It's not showing act. You can't see car or goat. It's just imagine that there are three doors. You don't know what's behind them. And you've chosen door one, let's say. So if you've chosen door one, then Monty will open one of the other two doors and show you that it's empty. I mean, nothing there, or maybe a goat. And say, okay, choose again. He allows you to choose again. Make a second choice. Now, in the second choice, your original choice, let's say, was one. You had selected door one. And Monty, let's say, opened door three. So, and showed you that there is a goat behind it. So you have one more chance to select. So let me just remember this is door one, this is door two, and this is door three. So player has chosen door one and Monty has opened door three. So this is out. Now Monty says, choose again. Would you like to choose the first door, which was your original choice? Or would you like to switch to the second door? So is it better to stick to your original choice or is it better to switch? That is the question. So what is your thought on this? Anyone?
Um, can I?
Yeah, please.
I mean, I think switching would be the better choice because, like, if you're to look at it purely from
Hmm.
probabilities,
Hmm.
so so if you switch, then like the probability of you winning would be like 2 by 3 of times. Like you win 2 by 3 of times.
But
If
how
you
do you know that?
so so for instance, if like any door, if I pick one at random,
Hmm.
1 by 3 is the probability that I picked a car, and 2 by 3 is the probability that it is a goat.
Correct. Huh.
And so like, and then like when you once you switch, then uh like so if I had already chosen the car, then like switching means losing. But then if I had originally picked a goat, then
Switching would be more beneficial.
yeah, exactly.
No, but see now see what you did, you suppose you chose door 1, okay?
Mm-hmm,
And Monty opened door 3 and it's out.
mm-hmm.
Okay. Now second choice, you will either win or lose, right? So in the second choice, you have a choice to shift to door 2 or door 1. Now there are only 2 doors. So shouldn't the probability be 50-50? I mean
So
half and
is
half?
the door opened and like, do we know that it is a goat?
Yeah, yeah.
Oh,
Yeah.
okay.
Monty
I thought
opens.
like the choice is given before the reveal of.
No. So first choice, so I should remove these pictures with these things. So basically there are 3 doors, nothing can be seen. Monty asks you to choose. You chose door 1. Okay. Monty knows what's behind the door. So he will reveal one of the doors which have a goat. Suppose he reveals 3 and you see a goat. Okay.
Mhm,
So that is out.
mhm,
Now you have only choice between, he says choose again. For every player, he allows you to choose again. So suppose now you have 1 and 2. Now he's asking you, you want to stick to 1 or you want to switch to 2. Now you have to choose. Right. So
yeah,
in
okay.
this stage, is it better to keep to 1, which was your original choice, or is it better to switch to door 2? You said your earlier argument was that you would prefer to switch.
Yeah, that was in the premise that I had assumed the door wouldn't be open. So you
Oh,
make a
okay.
choice and then like
Acha,
you
acha.
like yeah, you still get a
Yeah,
choice.
okay. No, so Monty has opened and shown you a goat in door 3. Now
Mhm,
says, ki, okay, now obviously one of these two have the car and the other has a goat.
mhm.
So most people say this. What do others say? What do others feel? Anyone else would like to? So many people say and feel that switching or staying with the choice doesn't matter because now there are only 2 doors. So obviously 50, I mean, the chances are half and half of getting the car or not getting the car, the price, right? I mean, that's the mostly and in fact, when this problem it came out in a magazine, and the editor of the magazine so everybody said it doesn't matter and all that. And then editor said, no, it does matter. And in fact, yes, you're right, Anushri, the switching is more beneficial. Okay. So then the editor wrote a whole explanation as to why switching is more beneficial, giving the mathematical argument. And there was a lot of argument with the mathematician said that you are a hoax and you are a fraud, you don't know what you are saying. Anyway, that's that story itself is interesting. So why let's see this. So one thing we know that Monty never opens the door which has the car. Obviously, they see Monty doesn't want the car to be revealed in the very first time he opens the door, right? So he will obviously open one of the doors which have got the goat or which doesn't have anything. And he never opens the door chosen by the player. So that is the rule. He doesn't open the door. So suppose you have selected door 1, he will not open door 1. So he will open one of the other 2 doors and he'll reveal a goat the first time. Okay. Then he'll ask you to choose again. And in the second turn, you might win, you may not win. What is the probability of winning by staying with your original choice? And what is the probability of winning by switching? That is the problem. So let's analyze this. So here it's a simple analysis with a diagram. So I'm not getting into the mathematics, the probability part. So we have, let's assume that the player has chosen door 1, right? We fix the player's choice. Okay. The car can be behind any of the 3 doors. It's randomly placed, right? So the probability of it being behind door 1, 2, or 3 is 1/3, 1/3, 1/3. Now, player has chosen door 1 and the car is also supposed behind door 1. What will Monty do? That means the car is behind door 1. Player, first time he has chosen door 1. That means the other 2 doors have goats. So Monty can open any one of the other 2. It doesn't matter because he has to reveal a goat the first time, right? So he has a choice of door 2, and because the car is behind door 1, Monty will open and the player has chosen door 1. So Monty will open either door 2 or door 3, and he doesn't care which one. So half-half is the probability, equally likely. But if the car is behind door 2 and the player had chosen door 1, right? Then can Monty open door 2? No, because he can't reveal the car the first time. And he does not open the door chosen by the player. So he has no option but to open door 3. Similarly, player has chosen door 1, and if the car is actually behind door 3, Monty has no choice but to open door 2. So in these cases, in the first two cases, the probability is half, 1/3 into half, which is 1/6 plus 1/6. And the total is 1/6 plus 1/6 is 2/6 or 1/3. These are the cases where the player can win by sticking to his choice, because his choice was door 1, and the car is actually behind door 1. So only if he sticks to his choice, he will win. And that probability is 1/3. And in these two cases, the probability is 1/3 plus 1/3, which is 2/3. And which are these two cases? These are the cases where uh, if the player has chosen door 1 but the car is actually behind door 2, so only switching will be lead to the prize, right? And similarly this case. So this kind of a tree diagram, we call it tree diagram or whatever, and diagrammatic analysis only tells us that the probabilities are not half and half, but 1/3 and 2/3. So how else can students who are slightly older students, so what they do is, what one good way to get them to do facilitate this process of is to uh, write out all possible cases of the car position, of the player's choice, and of the Monty opening the door. So what we do is we say, okay, why don't you write this a set of 3 numbers which indicate the position of the car, the choice of the player P, and the door opened by Monty. CPM. C is the position of the car, P is the door chosen by the player, and M is the door open. These will obviously be numbers 1, 2, 3 only. There are only 3 doors, 1, 2, 3. So suppose the car, let's say the first one is the door. Door means where is the car? Suppose the car is behind door 1, and this is the player's choice. If the car is behind door 1, player can choose any one of the 3 doors, 1/3, 1/3, 1/3. So let's say if the car is behind door 1 and the player has also chosen door 1, Monty has a choice of opening door 2 or 3, like we said earlier. So suppose Monty opens door 3. What is the probability of this happening? This particular option. It's 1/3 into 1/3 into half. But what are the possible cases? As you can see, the car can be behind door 2 also, and Monty can open, the player can choose any door, and Monty opens accordingly, right? So we see that there are probabilities which turn out to be 1/18 and some probabilities turn out to be 1/9. And there are a total of 12 such cases. So all possible combinations of door CPM, all possible combinations of CPM. So students listing is a very important part which we often miss out. Enumeration is very important in mathematics. So asking students to list out all possible combinations, which in the language of probability leads to sample space, all possible combinations. So they list out the door can be, car can be here, player has chosen, door can be here, Monty opens the door, and so on. Out of these 12, we observed that there are 6 cases. Can you tell me about these 6? What is special about these 6 ones which I have ticked? 112, 113, 221, 223, 331, 332. So the first 2 numbers are equal, right? That means the car position and the player's choice is the same. And in this case, the player can only win by sticking to his original choice. And the probabilities are 1/18. So 6 times of 1/18, which is 1/3. And the other 6 cases are cases where the player can win by switching. And there are 6 of them, and each has probability 1/9. So that is 2/3. So even using the listing out and checking each case, we can, without getting into hardcore probability, this is actually a problem which students learn at class 11, the conditional probability, because what you are choosing in your second, the player is choosing, it is dependent on the door that Monty has opened, right? So it's conditional probability. And therefore, this is where you would actually, so how do you convince people that it is actually 1/3 and 2/3? Of course, by doing that analysis, and you can do. So I am not risking going into the spreadsheet, but this is a snapshot of a spreadsheet. And very interesting. I wish I could just take you, but I might get into that thing of sharing and not sharing. So what we do is we simulate this on a spreadsheet. And suppose I want to play this game 100 times. So I can't, how will I do it 100 times? Actually asking somebody, it's not practical. So what I do is I simulate. So in column B, so column A is just a serial number. It's only showing up to 15, but I can do it up to 100,000 anytime, any number. Column B is randomly picking numbers 1, 2, or 3. So I have 1, 1, 3, 2, 3, 3, whatever I have. Let's fix the player's choice of door 1. Every time player chooses only door 1. We can randomize this also, but that leads to a more complex coding. In this, Monty will open one of the doors. So if the car is behind door 1, player is also chosen door 1, Monty can either choose door 2 or door 3 with probability half. So we use a conditional statement, if condition statement, to decide on that. And then we check whether the player will stay in this particular, if you look at the very first row, then how will the player win? The player will win only if they stay with the original choice of 1, because the car is also behind door 1. So it should be stay and win should be yes, and switch and win should be no. So these three things are just put by using conditional statements. And within a second, of course, once you've entered the data correctly in the first row, you just double click on the cell and all 100 simulations will come up. And then you count. So whenever we count, every time we do it, we see that the probability of winning by staying with your original choice is around 0 points. Sometimes it may be much less, much more. But if you keep doing this, you will find that slowly the probability of winning by staying is coming closer to 1/3, that is 0.33. And probability of winning by switching comes closer to 2/3, which is 0.67. So one is that then it becomes little more convincing because you're simulating and you're getting to see, yes, something close is happening to that. But of course, for students of grade 11, 12 who do conditional probability properly, we can actually prove using the laws of conditional probability that it is actually 1/3 and 2/3. Then there are very interesting variants of this problem, variations. Now I'm saying what, and this came from students. They wanted to ask this question that Monty, suppose he opens whichever door, he doesn't care, like suppose. But what if he has a bias towards one of the doors? Some people have this thing about numbers, lucky numbers. Suppose he always manifests a preference for door 3 over door 2 or door 1. तो क्या होगा? So the natural one student in one of the years when I did this problem with grade 11 students, they said others, when this person articulated this question, the others said कि अरे क्या होगा? Obviously change हो जाएगा, because now if the person is biased and he tends to open one particular door more often than the other two, then naturally the probabilities will change. So what will happen to the probability of winning by switching? Will it still be 1/3, 2/3? Or will it not? So this kind of a tree diagram shows the analysis. Now, if Monty has a choice, between door 2 and door 3, the probability of his choosing door 3 is more likely than door 2. And then they worked out, but very interesting that his bias had no effect on the probabilities of winning by staying and winning by switching. And we can prove just by this simple tree diagram, by multiplying the probabilities, that actually it remains the same. So it is still 1/3 and 2/3. And this is quite baffling because it defies your intuition, right? Because it should change, but it doesn't. And then some students wanted to know what will happen if there was a fourth door, So instead of 3-door problem, if it becomes a 4-door or 5-door. And a very interesting thing came up that the tree diagrams get more evolved and more complicated. But the idea of the 3 doors is done, then they can just extend it to 4 doors. And then you don't need to extend further. Basically, in the case of 4 doors, it was found that the probability of winning by staying with your original choice is 1/4, and probability of winning by switching is 3/4. See, there it was 1/3 and 2/3. Here it is 1/4 and 3/4. So can you guess what it will be for 5 doors? So it was 1/3 and 2/3 for 3 doors. For 4 doors, I'm getting 1/4. You can do the analysis, and 3/4. What would your guess be for 5 doors? So
1/5 and 4/5.
very good. And then it was not very, I mean, then students say, okay, suppose the n doors, generalized problem, abstraction, complete abstraction. So it will be 1 by n and
N minus 1.
N minus
n
1.
minus 1 by n. And this is amazing. It means that if you keep increasing the number of doors, the chances of winning by switching is much more. It is increasing. Because pehle 1/3 is the highest fraction, no, amongst all these. So probability of for 3 doors it was 1. But as you keep increasing the number of doors, the chances of winning by switching gets higher and higher, basically. So many interesting insights. Then there are many variants to this problem, and students were given the task of read up and come and find the variants. And there is some prisoner problem which has got. I mean, it's not it can be reduced. These are all analogous to the multi-hall problem. So they figured out that there was a lot of interesting presentations and all that. Okay, so I think I need to start winding up because I think there's a little bit of discussion at the end on computational thinking and its implications. But if I had time, I would also, this is a particular puzzle which I think everyone enjoys doing, and in BLED students observe this puzzle for in a different practicum, nothing to do with mathematics. But this is the Tower of Hanoi puzzle. So are you able to see me on the screen? Okay. So I'm not going to get into the discussion, but this is a problem which is really beautiful because uh, it 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 is truly a low threshold but a high ceiling task, because it just goes to amazing. You can take it to any level. And the initial problem is just that, you have, I don't know if you can see me, but so this is a wooden model of the Tower of Hanoi. What you can see, can you see me? Or
Raise it a bit.
Yes, ma'am, we can see you.
just, sorry. Can you see?
Yeah.
Yeah, but it's there on the slide. So what I'm saying is on the slide, it's a picture of a wooden model with the tower showing. What I have is a triangular one, but it's the same thing essentially. There are 3 pegs, and there are discs of alternate colors on one of the pegs. So the problem is that I have to shift the entire tower from here to any one of the other 2 pegs. But there are certain 2 rules. One rule is that I can only move one disc at a time. So wherever I go, I can only move one disc at a time. I can't pick up 2 discs and put them like this. That's the first condition. The second condition is whenever I am doing the movements, I cannot put a bigger disc on top of a smaller disc. So this is not allowed. So I can only move one disc at a time. So one disc movement will be one move. And I can never put a bigger disc on, this is allowed, but I cannot put a bigger disc on top of a smaller disc. So what is the minimum number of moves required? And there is a legend about this, also called the Tower of Brahma and all that. That is, there is a idyllic temple in Kashi Vishwanath, which has, these 3 gold pegs and 64 discs of reducing radii, and how much time will it take, how many moves will it take, and all that. Other than that, so let's just stick to the puzzle. So if this is the case, what is the minimum number of moves? Now, normally what I would do is I have 10 of these pieces with me. So I take them to class and I just ask students to sit in groups and they play around with this. Now, first thing is free play. So free play means that try it with 6 discs, and I've got, when I ask, okay, try to give me a not exact number, estimated number of moves. So as they start making the movement, so suppose the first is obviously the smallest one has to be picked up. The second one, you can't put it on top of this, so it has to come here. Then when you release the third one, it cannot come on any one of these two. So you have no choice but to put the smaller one on the bigger one, and then, so starting is not that difficult, but as you move, you tend to get confused as to where you have to go. So people have given estimates like 34 to 80. I mean, the range of moves required. So then we said, okay, now you need to simplify the problem. By simplifying means that you reduce the number of discs. So suppose there are only 2 discs. How many? So I have suppose 2 discs. I hope you can see. So then I want to move this tower of 2 discs to another peg. So what is the total number of, minimum number of moves required? So I can move this red one to one peg here. I can move the black one to the other peg. This is the second move. And finally, I move the red one on top of the black one, right? 3. So this is easy to do. So we simplifying the problem allows us to at least approach it. So then we say that, okay, so this is what it is. If there are 2 discs on one peg, let's say peg A, B, C, I need to move this to another peg. So let's say B. So I move the smallest disc to the third peg, then I move the bigger one to the middle peg, and then bring this on top of this. So essentially I have 3 moves. What happens if I add one? Now when I add one, now here is where the recursive thinking starts. So I know that to release the lowest peg, lowest disk, I have to move the top 2. Now suppose I move the top 2 from here to here. I can't pick them up directly. So that movement will take 3 moves because we've already shown that for 2 disks, I need 3 moves minimum. So 3 moves will shift these 2 disks to this peg. And 1 move will move this to this peg. And another 3 moves will be required to shift these 2 back here. Ultimately, a total of 3 plus 1 plus 3, which is 7 moves. So for 2 discs, it is 3. For 3 discs, it is 7. And then students are asked to tabulate and they see a pattern now. So here we see recursion happening because when we actually list out the number of moves required for a larger number of discs, we get to see that we can find the explicit rule, and we can also do it in terms of a recursive rule. A very interesting pattern comes up. You saw 3 plus 1 plus 3, right? In the case of 4 discs, it becomes 7 plus 1 plus 7. But 7 is the number of moves of the previous number of discs. So it becomes 2 times the previous number of discs plus 1. So you get a recursive rule also, and you get an explicit rule. And so I'll just breeze through this. You can prove this using mathematical induction in a higher class. In a slightly lower class, you can give them a counting problem also, that how many ways can you arrange these discs on the pegs. And these are some snapshots of students' work and what they were explaining and how they were representing their thought and ideas using diagrams. Then we reach what is called Hanoi graphs. So this becomes a part of graph theory, but the whole idea is that we can't keep drawing these diagrams. So from the concrete, I move to the pictures, the iconic mode. But from the icons also, I have to make it more precise and more easy to handle. I can't keep drawing this. So I just use these vertices and I join them with lines. If a movement is possible to, a single move is possible to move the disk from one state to the other. So this leads to what is known as, so this is just the case of one disk. We have only 3 The disk can either be in this peg or this peg or this peg. And there's a very simplistic situation here, which is called the Hanoi graph of whatever, 1, 3. But if you do it for 2, then you get to see a structure like this. And interestingly, if both the pegs are on, both the disks are on peg 0, and you want to shift them to peg 2, so you have to go from 0, 0 to 2, 2, and the shortest path is 0, 0 to 0, 1, 0, 1 to 2, 1, and 2, 1 to 2, 2. That is 3 moves. And we know that for 2 disks, the minimum number is 3. But what became more fascinating is that as students tried to draw the higher order graphs, that also looked like the Sierpinski triangle. So, that Sierpinski-like structure re-emerged. And these students had already studied about the Sierpinski triangles. So they were just, yahan bhi aa gaya, you know. And this particular student's work, the work she did in her file is that, with her permission, of course, I've taken a picture, that, there is self-similarity even here. And this led to amazing explorations of different kinds, Then even students looked at, I have done this even with maths honors students who study graph theory. So there, they have really got into the proper graph theory results and all that. But up to grade 10 or 11, and of course then 12 also, students are able to do this much, what I'm showing right here on the slides. And I've also written about this in Mathematics Teacher. So I'll just now conclude because I think we've taken a lot of time. So we were saying that these tasks, of course, the Tower of Hanoi problem does not use, at least I have not used any technology per se, except that to draw the Hanoi graphs, you can use some software. But even without that, so many of these tasks do not even need the use of technology. You can do them, you can design them in a way so that even in a context where you don't have any access to any digital tool, you should be able to do the task. So now the NEP has talked about coupling mathematics and computational thinking. So we need to think that what is computational thinking? A proper unified definition is still not there. It's still elusive. So computational thinking is considered now to be a broad skill set across contexts and domains, but mathematics seems to be the natural playground for it. A unified definition is still elusive, and when you ask people what is the definition, they say, okay, this is thinking like a computer scientist, which makes it a little problematic, because then are you saying that others cannot use computational thinking? So this is one definition. And when people are saying that, computational thinking is where you break down a problem into steps so that it can be solved by a computer. What is this computer? We need to understand computer in a more abstract sense. Is it this particular computer that I am sitting on? Or is it my phone? Is it any specific device? Or is it any information processing agent? Okay, it could be a human being. So basically, you want to instruct somebody to solve a problem, and you want to break down the problem into a step-by-step process. So we need to understand the meaning of the word computer. I mean, if we go by that definition, then we need to understand the computer in an abstract sense. And we should not confuse it only with computing technology and programming. So computational thinking is not only about that. Much of mathematics in school is about learning procedures. Like whatever we do in school, multiplying numbers, multiplying matrices later, solving a quadratic equation, proving an identity, all these require step-by-step procedures. Computers can do all of this. So CT should be about devising procedures. Like for example, in these problems, students had to think, how can we count? What can we do so that, we count more easily without counting everything? So devising procedures, understanding why they work, expressing ideas in computationally meaningful ways. So one meaningful way is that I count in such a way that I can count everything without actually physically counting. Can I use the idea of symmetry to count if I'm counting the triangles inside the Sierpinski triangle? But computationally meaningful, when I'm trying to get Excel to do it, I have to use a particular command in the right way. Otherwise, I will not get the correct output. So CT is about devising procedures, understanding why they work, but it is not only about using digital tools or coding or programming. Okay, so this now that this is a section which is saying that mathematics and computational thinking will be given increased emphasis throughout the school years, and they are recommending the use of puzzles and games. And I don't know if you have opportunity to look at the new class 6 textbook. That is they have integrated quite a few games and puzzles there with prompts as to how one could explore. But then there is a little challenge here because tasks which are for exploration tend to be open-ended. And sometimes teachers feel at a loss that how are we going to do this? How are we going to make students do this? Which is very relevant problem. And how are we going to assess? How much, if it's an open-ended task, assessment becomes more challenging because to what extent is any particular student able to do that? If you have to give marks, then that's a challenge. But at least this it appearing mathematics and computational thinking appearing in the document also points to a significant shift in the focus. Is that it's not just about learning procedures, but it's probably more about learning a way of thinking. I mean, that's what I feel. I would like to know your views also on this. And then, of course, if we talk about computational thinking, we cannot not mention the name of Samuel Papert, who way back in the 1980s, I mean, today it's not a new term. So way back in 1980s, he used to do experiments with children with turtle geometry. So there was to be this turtle and children had to give commands to make the turtle move in a certain way. And through this, in this book, Mindstorms, he talks a lot about different experiments with children and how that he actually introduces a computational style of learning geometry. And later on, this became a big term when Jeanette Wing, in her paper in 2006, short paper, she mentions about computational thinking and then she describes it. There she says it's like thinking like a computer scientist, but she also says to reading, writing, and arithmetic, the 3 R's, so to speak, we should add computational thinking to every child's analytical ability. In a 2008 paper, then she sort of she expands it and says what is CT? The thought processes involving formulating problems and their solutions so that the solutions are represented in a form that can be effectively carried out by an information processing agent. So this is a snapshot of that paper, a little bit of that paper. Then there are others like Stephen Wolfram, who was responsible for Wolfram Cloud and Wolfram research. He writes in this book of New Kind of Science, he's talking about computational thinking and its association with the physical world. And he argues that, we need a new branch of science to study that computational universe. And in fact, in a recent article, he says that if there's any domain or field X, there already is or there is going to be a field called computational X, So it's incredibly important to be teaching kids today. Computational thinking is to be needed anyway. That's any future career will have something computational. So typically, the key elements of computational thinking are said to be decomposition, where you reduce the problem into simpler parts. So for example, the Tower of Hanoi, we could not figure out for many disks together. So we reduced it to 2 disks and then moved to 3, then moved to 4. So that's something we do frequently in mathematics. Decomposition, then pattern recognition. So in a table of data, seeing the pattern, or in a solution of a problem, seeing a certain pattern and applying it to other problems. Abstraction is arriving at the solution to the more general problem. An algorithmic design or algorithm is to write the step-by-step procedures so that any agent can solve it. And there are other researchers like David Wintrup's groups, they talk about computational thinking skills like ability to deal with open-ended problems. Now, this is something which is not easy to achieve at all in school. Because if the problem, as I said, now the textbook is bringing some small open-ended problems, but we need to equip teachers as to how to do these problems in the class. Persistence and confidence in dealing with complexity. Another researcher uses the term computational thinking disposition, that if we want to make our students resilient and have that confidence to persist with something, because mostly, unfortunately, people want quick answers nowadays. But unless you struggle with a problem and you keep struggling with it, that persistence is important. And then only you get the confidence that, okay, if I continue with this, maybe I will arrive at a right. And in that struggle, you also get a lot of insight. Representing idea. Anyway, this is a list, but a lot of these we see are common to mathematical thinking skills also. So definitely there's an overlap. The PISA 2021 framework also has talked about the synergistic but reciprocal relationship between mathematical and computational thinking. But to my mind, I think, see, both involve problem solving, recursion, modeling, simulation, all this would come in the overlap between computational and mathematical thinking. But mathematical thinking is probably more about justifying solutions, arriving at proving results, and in terms of algorithm, breaking down problems into steps so that any machine can solve it, to some extent coding, all this would probably be more under computational thinking. And technology can mediate both computational and mathematical thinking, but again, the answers are not simple. We need to think a lot about how we can bring this synergy. And the biggest challenge is for teachers. Teachers will obviously be worried now. If we are integrating computational thinking in mathematics, does it mean we have to teach something new and extra? It should not be the case. It should be that the approach to teaching needs to change so that CT and MT are happening sort of simultaneously if possible. So what are the characteristics of good CT-MT explorations? That they are low threshold starting points, so something for every student to do, but the problem should have multiple paths of inquiry, maybe more than one solution. While engaging, you get some mathematical insights, even if you don't arrive at the final answer. Meaningful use of technology, engaging with processes of visualization, pattern generalization, pattern recognition, and so on. But opportunities for finding what I found in these projects and over the years, the experience that I've had working with students is, after a while, they start asking questions. I mean, they start thinking about things, what if we try? What would have happened if this was? So new questions for problem posing. Problem posing is something that we can bring in if we, and broadly, I would say that, to conclude, that students, they own their projects. They were proud about what they did. They to some extent they were responsible for their learning. They worked in groups. That is even something very wonderful. And while technology may have been an amplifier, and that we have to see, but there were the outcomes of many of these were not predefined. Even as a teacher, when I used to do something, I did not know exactly how it will turn out in the end. So there was always a sense of suspense, but many aha moments. Students asked what if questions, revisited mathematical concepts. And one of the things, of course, is now there are many fairs and competitions where students have to present projects, and also uh, every year we used to send some project or the other to these competitions. And whether they won or not is not the point, but they were presenting these ideas. And so curriculum, of course, we need to include mathematical modeling and applications in the curriculum at different stages. And discrete mathematics, I feel, should be there in the early school curriculum. More of, because I think towards, by the time they come to grade 11 and 12, it's much more of calculus. But discrete mathematics somehow gets neglected, where simple counting, listing, categorizing, classifying, these are important processes which sort of get missed out. Uh, and I think I'll just end with uh, this quote by Papert from Mindstorms only. We said, before computers, there were very few good points of contact between what is most fundamental and engaging in mathematics and anything firmly planted in everyday life. But the computer, a mathematics speaking being, in the midst of everyday life of the home, the school, and the workplace is able to provide such links. And the challenge of education is to find ways to exploit them. So this gives us food for thought, I think. And thank you so much for your patient hearing. We have time for questions or discussion, I think.
Yeah, Jonaki, thanks a lot. In fact, I was tempted to tell you that, just wind up in 10 minutes, but then I realized no. There are few, participants. They are willingly here. So why not we have full presentation? And it's brilliant, I'm a psychologist. I'm not a mathematics person. I sort of move the way Davida was moving, how a child sees the world and how a child makes meaning of the world. And then when we say that the child is actually mathematizing the world to also get certain kinds of meaning, to see the world in certain ways, the child is actually abstracting. And that child is theorizing. The final understanding of the world comes from that theorizing. And so what David was telling, that even in class 1 to 3, if the mathematics dialogue is always around that, the way the child actually looks at the world and thinks about it. And even at advanced level, when we were talking about computational thinking, it's sort of approximating what David was saying, but taking it to leveraging it to another level where it becomes a tool, you know. And that's again an invented tool, because it's a very abstracted heuristic or computational system that the student is getting to think through. So it's again building on his own capacity to think, and also what is around him and his thinking, and then creating enormous amount of tools to think through. And like here's just psychologists listening to you, a lot of mathematics students and scholars are listening to you, and we're just moving so beautifully together. No, it's really really brilliant. I'll not come in in the way. Let others ask questions. And we'll get Jonaki and Jayasri also works in this area. So we'll see how we revisit this particular, area once again, in yet another way. But let's take some questions or comments. Um, okay, now it's open to all of you. Please feel free to interact with Jonaki in whatever way, through questions or through comments, or any example you want to bring in, or how you connect to this dialogue. Please do so. Jess,
Yeah, Jayashree here. No, I'd like to come at the end. If there are younger people who want to ask questions first, let them. Otherwise, I just wanted to ask a question more about, Jonaki, I mean, have you been able to I know that you had done a lot of this work when you were, in the school in Delhi public school. I think you had already experimented good bit. But now, I mean, have you been able to get a set of schools, and particularly a diverse set of schools with whom it is possible to do this kind of experiment? I mean, using
Yes.
technology in the classroom.
Yes. So one, of course, I keep doing these with my first year students because they come from a diverse background. So we get about 60, now almost 80 students come from different kinds of schools. And we don't have good access because I cannot take 80 students to a computer lab. So,
Right.
I try to do things more which are accessible on phone. So in college, the advantage is that they can bring the mobile phones to the class. So we use spreadsheets on the phone, we use GeoGebra on the phone, and we also use this one open source tool called Mathigon on the phone. So that has been there, but the level of the mathematics cannot go beyond a certain level because the students are not doing calculus or they have not studied maths. Some of them haven't done maths in 11th and 12th. So it's more to do with the discrete math kind of things are the more things they can do at this stage. In school, yes, I have approached certain schools. very often it's hard to get students of 11th and 12th, but grades up to 10, 9, 10 middle school. So there have been different, like once I did a little project with grade 6 students. So I spent some time in that particular school. So not all are like DPS or any other, not all the schools are fully resourced and this thing, but also I mentor some students who work on math projects. So
Okay.
there are many students. So there is this thing called IRIS, Initiative in Research and Innovation in Science.
Okay.
That's an international fair. There's a team India which goes to the international fair, but there is a national fair before that where students across schools they send their own maths projects. But those are, of course, over the years, I'm finding that there are many students who work with certain mathematicians and then they do very extended work and then they send projects. But earlier, we used to find students who would look at some problem in their day-to-day life and make a project out of it. And so they are very interesting experiences that I have had, and they're quite people from varied backgrounds. Yes.
Mhm. No, yeah, but then schools themselves in the state doesn't give you permission to work with some schools where you directly kind of in Delhi itself it doesn't happen much. That's what I'm asking.
No,
Not with individual
not on a
schools
very
where you
large
are.
scale. No,
Not
and on a
not
large scale.
large scale, but a kind of a project that the state takes up. You are doing it
Yeah,
as an individual researcher
correct,
who's,
correct,
I
correct.
mean, yeah, we are
Yes, yes, yes,
at level, yeah. Just was curious because much is
yes,
happening in Delhi.
right. In fact, there was one, I had a conversation with SCRT in Haryana because we recently had this conference with them. Jointly, we did the conference. So we were exploring if we can do it here in the state of Haryana with schools and but they said if you would can do something with middle school students first before you do with the higher classes, it would be better. So there is opportunity to do that. But what I feel is that ultimately everything boils down to uh, one that how do you facilitate all this? So the on the screen and on this the ideas look good and interesting, but you have to work with the students and one of the pitfalls of this thing is like I went to the school with grade 9 students. I did this experiment. I needed there were 25 students and I needed four sessions of 2 hours, 8 hours to do
Oh,
this particular problem, the house number problem, the Ramanujan and Mahalanobis thing.
okay.
And there, because that exploration leads to, the Pell's equation and all, so leading them to that, but they did some exploration on spreadsheets and exploring polygonal numbers and things like that. So it took so long, but ultimately the result was fantastic. I mean,
Mm,
how their trajectory of thinking, if you have to observe, then
mm,
you need to engage with the students at least for 3, 4, 5 sessions, at least to the
mm, mm,
minimum.
mm,
But that kind of time as a researcher I may have, but how do we bring it, how do we scale up this? That is definitely a challenge. How do we do it on a large scale thing? If you
mm,
now came up with a book which has a detailed discussion of these things. It's written in the form of exploration, investigative approach.
mm,
So the
mm.
hope is that students will take up the book and pick up problems from it, explore.
Okay.
But then it should not become like a textbook. Like, if we do this on a large scale, it should not be that someone comes up with a textbook and says, okay, these are the solutions. So that
Mm.
danger, then the discovery approach, the inquiry-based
Yeah,
learning will not happen.
sure, sure,
So, yeah.
sure.
But I'll be most happy to get ideas from you
No,
as to
no,
how
not
we
from
can
me.
do
But this is
scale up.
really, I mean, this whole potential. I do a little bit of exploration in the class. Try to tell them, like solving linear equations. You can actually almost always turn the Gaussian elimination into something that you can do on a spreadsheet,
Ah,
and
ah,
then you can keep changing the numbers, and you just really. But I
hmm.
have rarely found students doing it also, unless I really force them, I insist that you do it on, and I'll grade you only the Excel sheet or something like that. They don't.
Yeah,
I have not been successful in enticing them to use technology.
right. In fact, one of the assignments that I give my first year students, I don't know if Isha is still here and she remembers or not, but is a project, exploratory project. So 50 marks, 50% weightage to that. They have to work in a group and they have to pick up one of these problems and explore it. And they're not, I mean, they can do some research, whatever they want, but they cannot, I mean, I want to see some actual mathematical exploration handwritten on their project report, and they have to present it to the class. So this year, so they all study these fractals and also, and they also learn about tessellations and different kinds of tessellations, and they
Ma'am,
look.
tesselation we did. What exploration are you talking about?
So this year's batch has been asked to explore if fractals can be used for tessellation.
Mm-hmm.
Okay.
So fractal, one particular stage of a fractal cannot tile the plane, but can you merge different stages of the fractal and cover the plane?
Mm.
There'll be a lot of geometry, there'll be a lot of exploration, and they have to also
Okay.
justify why, if two or three stages are tiling the plane, then why the particular choice. This is what it came out because they said, ma'am, we like fractals, but we don't know what to do with them. So then you have to give them some ideas. Okay, why don't you do it this way or that way? And there's another group which is doing something
I've just
completely different.
forgotten.
Hanji, sorry.
I've just forgotten what we did. It's 10 minutes.
No, that's because we don't get to do them again.
Yeah, yeah.
Technology will not stay on, but it will come back if you try to do a little bit.
Yeah, many of them didn't even use any technology actually. Many of the projects are without this thing. So if you're doing some exploration by hand and you're actually drawing pictures by hand, they may use a software tool to replicate it. And like for example, tiling has become very easy now with Mathigon, for example. You can make
Mm,
multiple copies and place
mm,
them and move them
mm,
around. So that
mm,
is just an add-on.
mm,
Uh, Exploring Escher's tessellations and how
mm,
did he arrive at those modified tiles
mm, mm.
and creating your own modified tessellation. So these are the things geometrically students can. Geometry is something that is still well within their purview. Uh,
Now, when you're talking about tessellations and this thing, it just, I mean, this whole simple idea of calculating the area of an object. Now, using
mm,
fractals,
yeah.
so you say, for example, to find the area of a rectangle, for example, you're going to put so many squares in it and count the number of squares. Right now, that doesn't fill up the whole space. There is so much more left. Now, what do? Then
Mm,
can you actually take a fractal part of that square and
mm,
do it? And so if you have a irregular space also,
mm,
fractals may actually provide an interesting intermediary
yes,
between calculus and
correct.
isn't it? Don't you think so?
Yes.
We can actually experiment with this. I just occurred to me when you mentioned the term tessellation. It occurred to me that we could actually use in
Because that is what Mandelbrot also says, no? The coastlines are so only thing is that so if something is jagged, I mean its
mm,
boundary is not smooth.
mm.
And how are we going to measure the left out
Like
portion,
exactly,
like you
this is a
said?
generalization. Yeah, that's right.
Yeah, yeah. So I think there is plenty of scope to ideate and bring out new ideas, but how do we scale this up? Like how do we do it on a large scale?
That's
I
true.
mean,
Yeah.
that is a challenge. Any suggestions from anybody else who has?
Any question or suggestion that she's asking?
I had a couple of thoughts, if it's okay. Yeah.
Yes, yes.
First of all, thank you so much. It was a really amazing talk, like after a very long time. And so I was wondering about a couple of things. So first of all, I was thinking about how we could understand both computational thinking and mathematical thinking in relation with, so especially with the emergence of socio-ecological in mathematics education research very recently. I was
Mm,
thinking about how we could contextualize this for students, so when you talked about fractals, we started with how they occur in the nature, And I've seen teachers who attempt to do similar things in classrooms, but like it doesn't get fulfilled, or like they do not stick with it till the end. Like you mentioned that there are patterns, and then you leave it there, and then like it becomes purely mathematical, and like it has to do with symbols and stuff, and then the nature and like context is left behind. So I feel like what could be done to bring it back into classrooms. And the other thing I was actually wondering about is, so these are like really amazing discussions, right? Like these discussions could be extremely useful in classrooms, but for some reason I feel like these discussions get constrained, or like it's restricted within the researchers. Like like I'm just thinking out loud. I'm like, how do we get teachers involved in these discussions? Like like, if is there a platform for teachers to be a part of such discussions in talks, so that they also get to experiment these things in their classrooms? Yeah, that's it.
Yeah, I think one of the important things, and that's what MTA is also encouraging, is that starting with study groups, discussion groups or study groups, where teachers come together and everybody comes together, mathematicians, teachers, uh, college teachers, school teachers, come together in a study group to explore one particular theme in depth. And then see, if as a teacher I have the wherewithal with me, then I will find ways to bring, like you said, no, if there's an example of nature, and then it's just that nature is so complex. The complexity that we know is that young children cannot, probably they will only self-similarity, I can explain them by, okay, I can enlarge this, it looks like this, but I cannot get deeper into it. With older students, I can say, okay, look at these fractals and look at their dimension. Let's understand what do we mean by dimension. Now, dimension has been redefined. Now, the
Mhm.
dimension of the Sierpinski triangle is some 1.6 something. So, the
Mhm.
dimension is fractional. So, at a slightly, so a theme has to run for some years. I mean, at grade 6 or 7 or 8, they can just do some drawings and exploration. And grade 9, you could go a little further. And then when they do calculus and other things, then they. So a strand has to run across. Maybe we select 2 or 3 or 4 of these strands where we show mathematics occurs in nature, occurs in various, is there in all phenomena. Pick up certain themes and carry them into the curriculum. Then only I think it will be fruitful, because it is obviously not possible to do everything, but one or two, I mean, 3, 4 things should be there. But I've also been a part of the exercise of the textbook writing recently.
I was about to ask you.
Ah, and there it's so difficult because we are thinking of framing the class 9 syllabus. We are doing that now. We're trying to bring a change from what it was. What was what was there was fine. I mean, it was just that we need to do little differently, the change in approach. But again, we get into that mathematicians will say this approach. You know, if you look at the curriculum of the IB curriculum, if you're familiar with the International Baccalaureate, it's the elite schools are running the. But if you look at the curriculum, it is very differently organized. Like I was sharing what the big ideas. So their topics are not, chapter names are not arithmetic, algebra, this, that. There will be a whole set of chapters on the theme of equivalence. So they've used the big ideas and equivalence, using equivalence, they are cutting across different topics.
Mm-hmm.
So students are not looking at, oh, acha, ye arithmetic hai, ye algebra hai, or teachers for that matter. So they have designed, the design of the curriculum is very, and to agree upon an appropriate design becomes very difficult in big groups where, obviously, where sometimes, if I may say so, that what are the challenges of the teacher in the classroom? So one has to, so in the group, we must have mathematicians, we must have teacher educators, we must have teachers also who are facing this every day in the class. And we have big groups. But coming to a common this thing about what should be and what teach, we can't squeeze in everything because there are pressures of how many pages can be there in the book and all those things. There is a there is a big thing about, oh, children at this age cannot do this. I have myself not believed in that actually. I have always felt that children of any age can do anything, almost anything. It all depends on the, but again, when we are creating a curriculum for everybody and one size has to fit everybody, then of course there are certain ways we have to think. We can't be idealistic and just do anything. But what I'm saying is a very challenging exercise. So even when that I wanted to suggest, let's do this, it works if you do it this way. But others might feel that, oh, it will not work with everybody. So that challenge is always there when it comes to uh, designing the curriculum, writing the books, and but I think what they are suggesting now, and one idea that has come up is we will have in each textbook there will be a set of pages at the end, which will be that high ceiling thing, you know. So the chapters will have something which everybody should do or can do, but that those pages will indicate readings, it will indicate if a student wants to explore further. A student for whom only the textbook is the resource should have the opportunity to read further. Somewhere we are thinking of giving a QR code and providing more information, but QR code again can be accessed only if someone has a phone. But at least suggest certain readings and start off something and say, okay, if you want to explore further. So whether it will work out in the end, I don't know, but there are thoughts like this. Just wanted to share. Yeah.
But the thing that one could probably do, should need to do, is with the teacher education programs, I think. No, now this 4-year teacher education program that the state is talking about. I know that you. I mean, I heard from Jam about this thing. That anyway, I mean, whether
It's
it is
very
bad, whether.
worrisome because maths is dwindling, diminishing like anything. I don't know what's going to happen. I just don't.
But without teacher education programs where teachers are actually given hands-on, solid experience in doing these things, we cannot expect that this will ever go to the classroom. This is my feeling.
You are referring to what Felix Klein said, no? Double discontinuity.
Yeah.
So we all studied maths in a certain way.
Mm.
Then we studied maths in college, right? Which was
Mm,
completely
mm,
different. We
mm.
studied maths when we became teacher educators. We thought we had to teach maths in a certain way. But when you go back to school, you again have to teach in the same. So there are two levels of discontinuity, I think, what he
Mm,
says. But
mm, mm, mm. But still, it's, I think, very fascinating, the
Yeah.
idea of being able to use.
And Jonaki, what I see is that there's a huge motivational issue, involved in this. And that's also because, these discourses are very linked. If they are engaging certain kinds of discourses in class 1, 2, 3, 4, or 5, they'll be able to, think in the way you are, you know, expecting them to. And they'll also take those trajectories, And it's not difficult to do, just that um, teachers of all the levels have to sit together. So basically, at the time of curriculum making,
hmm,
preparing a teacher training curriculum or program, both pre-service and in-service teacher training programs. We also have to see how different levels are talking to each other and
correct,
how
correct.
the thinking is developing. So
Hmm,
what develops in the early stage actually becomes a sort of the I'll not say foundational, that's not the right word, but they provide tools to think with and think through. But then one has to see those connections. I think that is missing. And the reason why that is missing also is because we don't think, say, teachers of early mathematics need to know mathematics very well.
hmm,
Anybody can teach.
correct, correct. Yes.
थोड़ा काउंटिंग सिखाना है, एडिशन सब्ट्रैक्शन सिखाना है,
Hmm,
थोड़ा पैटर्न रिकॉग्निशन सिखाना है, but that's not mathematics. when a mathematics dialogue is different, I think what is fundamentally lacking is creating mathematical, discourse at all levels is fundamentally absent in early years. And by that time, we talk about class 9, 10, 12, 11, 12. Many students, you know, lack this
Yes,
capacity. I'll not say
yes.
capacity, even the desire, because they're not able to see many things, what we want them to see. So the whole discourse becomes a little alienating or intimidating to them, whereas it is immensely possible for them to travel with, even when their exposure is not adequate in earlier classes. We create a kind of lack of confidence
Hmm.
because this. So I think the curriculum and teacher training, they need to be thought through very differently. And that's where I think teacher preparation is poor. And when you say mathematics is dwindling,
In
yeah,
the teacher
I,
education program.
yes, in the teacher education
That's
program.
that.
Very sad.
I don't know, Jayashree may be remembering, a lot of things that we were discussing in late 90s and early part of, say 21st century. We are revisiting them and they need to be revisited. They need to be all the time discussed. It's not that we have discussed once, so we'll not know. It has to be constantly discussed and engaged with. But every time we realize that we haven't progressed much. That's something that's something very discouraging. Um, so my question is, like when you talk about, like suppose in BLEd programs, students come with different understanding of mathematics, different kind training in mathematics. So your classroom is hugely diverse,
Hmm.
except that if somebody doesn't have mathematical skill, that same person may have other kinds of linguistic and other kinds of registers that can
Hmm.
scaffold mathematical thinking. And those registers develop, those heuristics develop even in other domains. So there is a kind of cross domain, they just help, in also imagining mathematics. Even if that student hadn't done mathematics very well, but the student has other kinds of capacities and they help.
Hmm.
But then you deal with enormous amount of diversities.
Yeah. Yes.
So how do you deal with this question of, bringing all of them on board to engage with a dialogue? So there must be something that is happening before you get them fully participating in that dialogue, and traveling with those abstractions. So I think if one reflects on that, that also helps in how to then create linkages between, primary, middle, whatever now the new nomenclatures, new stages have come. But does NCERT talk about all these? I mean, when you go there, so like when they were discussing class ninth textbook, were they discussing if the students are, at least discursively ready to engage with it? And yeah,
Yeah, actually, in the first the syllabus framing, like right now, initially the middle school, the primary was working separately, but there were some meetings to discuss what was going into class 5, obviously, so that there's continuity in class 6. And after 8 and 9, so in those ends of those stages,
yeah.
they have tried to ensure that there is a trying to make it more seamless. So a lot of time has gone in this time to frame the syllabus itself. So by framing syllabus, it's not listing out the topics only, but
Mm,
what will be the we're thinking of a teacher handbook also. So like what kind of, so in the syllabus itself, there is a suggested activity. So if you have to achieve this outcome, then what are the kind of what should the flow be? What should the activities and what kind of questions should be asked? And later on, that becomes a framework for the textbook writer to refer to. So we're
mm,
trying to make it more seamless,
mm.
but and also there has been an attempt to make it more less topics and more in depth into some topics. I mean, there's an attempt, but I don't know how much it
Present.
will succeed. And but now that the class 6 book is out with 10 chapters, teachers are finding it difficult. I mean, the feedback that we've got, though more extensive feedback needs to be taken, but teachers are saying that it looks very nice and there are a lot of patterns and explorations, but how to, how do we go about it? It's not very clear. The earlier book used to have exercise 1.1, 1.2. So now try this out, So it's not written in the traditional way that, so we need some hand-holding and large-scale hand-holding, and teacher programs have to be there to, discuss with teachers that this was the rationale for this particular, including this particular idea or concept in this manner, and maybe you can take it forward this way, or so I think that will be an important thing to do.
Are they concerned about PISA tests simultaneously with this sort of
Yes, but not much. I mean,
not much?
recently
That's
the discussion hasn't hovered around that much, but yeah.
Any other question or comments? Yeah, it has been a long session. Uh, I mean, since there are few, if you have any question or comments, please ask. We'll wind up in 5 minutes if you have questions. Otherwise, we'll wind up now.
She has
Darsha,
shared
you have
some
any
link.
question? Jayashree, I'll get Jayashree on board even on this. I will talk about this. Jonaki, Jayashree together can have a dialogue. Like suppose when we talk about computational thinking and mathematical thinking, what I say is that as a psychologist, I see that the what differentiates these two is mathematical thinking. We fundamentally see it as something that the people are doing, but then what is outside me is also created by me. So this mind has both the outside and inside, and if I go by that definition of mind, they actually merge. They are not two separate one. I mean, one is getting trans. No, therefore I'm not rejecting it. What I'm trying to say is that the affordances of the concepts can be imagined differently if we attend to these kinds of things. But we'll engage with this. It's a very interesting area, and I think let's three of us can discuss and see how we can have another very interesting session on this. But what I see with Jonaki's talk is that it's not about just one concept and one level she's dealing with. You're traveling all through, the stages of curriculum, the different ways of linking with relating to mathematical concepts, ideas, or even the realities. So this is wonderful, actually. So I see a huge scope for a very rich dialogue. So we'll come back again on this topic today. Janaki actually motivated me to think of another session on this, and where let's have both Jayashree and Janaki together. And we'll discuss and plan it in a very interesting way. And you were talking about this IB thing, I'm also getting excited about. I'm also a macro psychologist, I mean, micro you can't understand till you have a larger picture. So these big ideas in IB curriculum, they actually provide you some of the nicer ways of doing mathematics, not in terms of doing, I mean, defining some topics and doing through those topics, but a kind of very circle, I mean, very deep discourse. So I think let's get back on this theme again. We'll have one or two more lectures before that. I don't want people to be tired with one kind,
Yes.
but we'll come back. Is that okay with others? There are a few people, but yeah.
Sure. Yeah.
I'll also talk to Jayashree. All of us have to be together to do this also. And I was traveling. I was
Yeah.
badly occupied, but I will this month I'll plan. I'll put few things in place. So I'll call you and discuss with you. So, Varsa, would you thank
Yeah,
Oh, it's okay.
I would like to
Yeah,
share a few things. I attended the MTA workshop in 2022 January, and in that both of you presented. I attended both of your sessions. That's how I got to know about MTA. Ma'am again in that presented about the Sierpinski triangle. That same problem that I had, and so when you were presenting, I immediately remembered. Okay, I did this before. And with Jershi ma'am also did a very hands-on experience. We have worked on an activity where we were working with the, you know, the whole geometry box. Uh, yeah, it was
right.
amazing
It's
listening to you, ma'am,
something I don't
today.
remember. Okay.
No, I remember because I attended the workshop.
Okay.
Yeah,
Okay.
yeah. So,
ऐसे आ जाओ दिल्ली. Are you planning to come anytime? JNU
Delhi.
doesn't have money, so I really can't plan a
No,
travel.
I mean,
We are
maybe
poor. We
I
are the
was,
poorest now, not
I
poor.
don't mind coming to Delhi anytime you call me, I'll come.
Yeah,
One
no,
day or
That will
two.
be
we are
nice.
below poverty line now, you know. We can't even support ourselves.
So we can,
So,
I have some funding to travel within.
if we are
So,
traveling, let me know.
sure,
We'll plan
sure,
something.
sure,
mm,
sure.
Ah,
Yeah.
Chalo, thank you then,
thank you,
Versa.
ma'am. Thank
Thank
you.
you
Yeah.
very much. And Saturday afternoon, everybody spends such a lot of time. Thank you so much. It's for me also, it's a great learning because unless you discuss, you don't get new ideas. So, and in fact, I was when I was selecting what problems to choose, I did not want to choose surface because there are so many beautiful factors one can discuss. But this is the one which gives the entry into the topic of fractals.
Mm.
And this theme can cut across various concepts and various levels. So if teachers can be exposed to this, then we can go to the discussion of what should be included at what level and so on. So I think,
This
Yeah.
is beautiful. Thank you, Jonaki.
okay.
Thank you.
Much,
That
ma'am.
person
Thank
to
you,
That's
have
it.
everyone.
you
Thank
on board, and we'll upload all the lectures on our website. So we're creating a separate website for mathematics because
you. Okay.
it will be linked to NMRC, but a separate website so that everybody can, get it. So that's something once Barsa comes back, so this is the month we'll be doing all this, you know. Okay, thank you,
Thank
Jonaki, and thanks everybody for
I have been
joining
you.
this
Thank you.
wonderful
Thank
talk.
you, ma'am. Thank you.
And
Thank
we'll
you.
be doing another one very soon. Ravi has given a date in early March, but February we'll have another speaker before Ravi.
Okay. Okay.
Thanks,
Thank you.
and then probably Jess and Jonaki will come back after 2, 3.
Okay, great.
Thank
Thank you
you.
Ma'am,
so much.
Rashmi Pal has asked that can we find any textbook from where we can get computational thinking ideas?
Yes, a book. Yes, I can share. I can write to you on
Share with
WhatsApp.
us. We'll share with us.
Maybe you can do one thing, Rashmi. Please type your email address and I will reach out to you. Okay.
Is
I'll
it Rasam Pal? Yeah, Rasmi Pal.
Rashmi Pal. Rashmi Pal.
Are
Rashami,
you there, Rasmi?
you can unmute and yeah, speak.
Rasmi, are you there? One of my senior student was Rasim Pal. Is it the same one or somebody else?
R- you can unmute.
Rashmi.
Rasham.
Okay, so from Assam. Okay, Jonaki, you send us. We'll
Yeah,
share
sure,
it with
sure.
them, and we'll
Definitely.
also upload few things which they can check. Yeah.
Okay, sure.
Bye then.
Bye bye. Thank you. Bye bye. Take care.
Thank you
You
for your
Get
too.
well soon,
Thanks
Varsha.
again.
See
Bye.
you. See you, Manasi. Okay, bye.